Thank you. All right, cool. Yeah, thanks again for the invitation for the tour in the morning and the opportunity to present my work here and maybe even collaborate in the future. Today, I'm going to talk about recent progress that we have made as a community in order to build autonomous systems. But I'll also talk about challenges that we're currently facing. And I'll argue why we haven't accomplished our final goal yet. From my research, I will share some recent trends and insights in the first part of the talk and how to make systems safe and reliable. And on the second part of the talk, I'll talk about how we can analyze robustness of systems, specifically temporal robustness. Okay. So first off, what are autonomous systems? Autonomous systems are engineered systems that operate in complex and open-ended environments. They perceive the environment and they learn and reason from data, and they act in order to achieve a wide variety of tasks to advance society and improve life for everyone. And autonomous systems research in particular promises to enable many future technologies, of which I guess you've seen most of them here, from the automotive industry, self-driving cars, manufacturing, in healthcare, in aerospace and robotics applications, in agriculture, connected cities, and automated services. Okay, and this really illustrates the potential impact that autonomous systems may have in the future. In particular, over the past years, the wide availability of data coupled with the computational advances in machine learning and AI have really accelerated the progress that we have made in building these autonomous systems. I'm sure you've seen all Tesla cars, but potentially also the Boston Dynamics robots, or here a drone fleet from the Kumar lab at Penn, where all of these autonomous systems really perform highly challenging tasks with ease, right? So the question then is, seeing these successful demonstrations, do we have all the tools and theories in hand to build autonomous systems that are also safe, right? And does it? Oh, I think it stopped here. Somehow okay, let me just maybe reconnect. I think I need to restart the app.
It doesn't work.
Yeah, it crashed. It showed an error message.
I see.
Yeah.
7-4-6-3.
Maybe the video killed it.
Just share it again.
Okay. Okay. So the question that I posed was, do we have all the theories and tools in hand to build autonomous systems that are also safe, right? That's where we stop. And as you can see here, that the answer to this question is probably no, right? Because at the same time, we've seen a lot of examples of Tesla cars that go high wire, of Boston Dynamics robots really failing over here, and also the drone fleets crashing. Even from, I guess, your experience in the lab and my own, for each successful video that you see online, there may be 10 or more videos on our hard drives that show behavior that is not successful, right? So the question then becomes, how reliable and safe are these systems really, and how robust are they, right? And I guess all of us had the hope a few years ago that autonomous driving would be a reality by today, but we all know this is not the case as of now. Even worse, I mean, the industry has reset expectations to only level 4 autonomy, meaning autonomy only in controlled environments, for instance, at airports. This has led researchers to instead focus on more solvable problems, such as autonomous boats, here, for instance, from MIT. So what are the reasons for that? One reason is that it's claimed that the way that we train our AI seems to be fundamentally flawed, right? So we tweak our algorithms in lab-like environments, but we're not able to make the transfer outside the lab, so to have robust algorithms, basically. Another reason is that it has been shown that neural networks and hence AI is easy to fool because it's not necessarily robust. Many of you have seen this example of a panda that by an algorithm is classified as a panda, but if we put some small noise on top, the resulting picture looks to the human eye really the same, but now the algorithm suddenly says it's a given, right? So the question then becomes, how can we make these systems reliable, safe, and robust? And also, what are the fundamental limitations that we're facing? And what are the formal safety guarantees that we can provide? Okay. And I know all of you guys are doing research. This is my autonomous systems research agenda, my personal one. I'm working on data-driven control, so we can chat about this also after. And the first part will particularly be about how can we learn safe control laws. Also during my postdoc, I work on risk-aware autonomy. This will be the second part of today's talk, so time-critical system verification. And my PhD was on formal methods and control, so if you're interested to chat about that, we can also do that later. And I've also worked on distributed autonomy. And my recent interest is also on human-centered AI. Okay, so this is what I'm also going into. The dimensions that I'm operating on is a system dimension here. So along this dimension, the systems will get more complex and potentially several agents will be involved. That's what I focused on. There's a specification dimension starting from simple spatial specifications such as safety, and then going to temporal logic specifications when timing plays a role, right? Temporal ordering, deadlines, and so on. And then for me, environment really matters. Do we know the environment? Is it unknown and dynamic, and are humans involved? Okay. And also just to give you an idea what my tools are, I have a background in model-based control and a strong background in temporal logics and verification. And I'm also blending in tools from machine learning and AI. And of course, as you can imagine, I'm working at the intersection here. So this is kind of the space that I'm operating in. For me, really important, that's the last point I wanted to make before I jump into the first part of the topic, is robustness. So I'm using several notions of robustness in my research for various reasons. First, it allows to integrate tools and theories from these different areas in a correct manner. But also robustness is something we're certainly interested in when we want to make the transfer to outside the lab. So robustness is always something we're interested in. Okay, so let's jump into the first part of this talk, which is about learning safe control laws from expert demonstrations. I've shown these three axes before, so we will operate here from simple to complex systems, but for simple spatial safety specifications, and we'll look at known and unknown environments. So this is at the intersection of control and ML. Okay, so and I would now like to shift the focus again to safety critical systems, which are really systems where a failure of the system can have catastrophic consequences, can result in the damage of property or even in the loss of human life. And unfortunately, we had to observe several of these incidents in the past. Uber accidents where unfortunately even humans got killed, but also drones colliding with airplanes, here in this case, where luckily no one got hurt. But the point that I want to make is really that system safety is the most important thing when we're dealing with safety critical systems. So how can we design safe systems? That's the question we want to answer now, okay? In general, a system is safe if its behavior is safe. The temporal logic people of you know, behavior can mean a lot of things, right? We're looking at a very simple kind of behavior over here, and we say that a system is safe if we can control it to stay within a safe declared set C. Okay, so it means nothing more than if we have this small robot over here and we consider this blue region to be safe, so there are no collisions, then our system is safe if it can operate in there to do some tasks, but at the same time will always stay in there. Okay, so that's the kind of objective that we look at. And of course, the control community has looked at this problem like from different angles, starting from handcrafting safe control laws, but this is typically limited to simple systems and also doesn't give us any safety guarantees in most of the cases. There are sum of squares programming approaches, Hamilton, Jacobi, Bellman reachability, and also discrete program synthesis. But here often one has scalability issues, and to solve these formulations, often approximations are needed. And then successfully used has also been not model predictive control, which, however, may require potentially heavy online computation. So in summary, finding safe control laws is challenging, especially if we talk about complex systems. And the question that we ask ourselves is, can we leverage data and use machine learning to find safe control laws? All right. And if we look at these three safety critical systems, then to us, it may appear at first that these systems are very different, especially in terms of their dynamics. However, now when we, like, in order to tackle that problem, I want to make the point that when we're talking about safety, we can argue about these systems in roughly the same way in terms of safety, right? First, these examples here are all really data rich in the sense that it's easy for us to get access to data that exhibits safe system behavior. For instance, if we're talking about autonomous driving, Uber has a lot of data with human driving behavior that shows safe driving. So we can use that, and we will do that here. Second, the dynamics of these systems are really inherently nonlinear and hybrid. So they're complex nonlinear systems, maybe even hybrid, meaning that the motion of the system is continuous with potentially discrete events. For instance, if the foot here hits the floor, the velocity will flip side. And third, and this is certainly a very important point, the dynamics of these systems is mostly well understood, right? So we can have accurate models of these systems using first order principles or system identification. All right. So what we want to do here is we want to use the availability of expert demonstrations as well as model knowledge to learn safe control laws. Okay? And at first, before I go into the details, I want to show you a high-level overview of our approach. We assume that we know the dynamics. We can relax that, we will in fact, but for now, let's assume that we know the dynamics, which are modeled here by an ordinary differential equation, and F and G are known, and U is the control input of the system that we want to design. Okay, so this is the first thing we assume to know. The second thing we assume to have is, like I said before, a set of expert trajectories. And they're indicated here by these spaghetti trajectories, right? And we assume that these spaghetti trajectories, these expert demonstrations, are safe, meaning that they evolve within a safe set that I've indicated here by this red box. This could be the set of all positions where we don't have any collisions, right? So basically all our drivers demonstrations don't have any collision. And what we're doing then is we're using our dynamics as well as the set of expert demonstrations, and we feed it into a constraint optimization problem that I'll explain in a few minutes with a goal to learn a safe control law. How do we do that? Basically, first, we want to learn a function from these two things that under approximates the operating regions of the expert. So we want to learn this blue region. And then on top of that, we want to learn a control law that allows us to operate the system in here safely. So not leaving the set basically while doing another task. Our contributions here is that we can provide formal safety guarantees for our learned safe control laws in terms of the density of the data, as well as the smoothness of our system and the function that we learn. We can handle perception uncertainty, as I'll show, and we can even do this for partially unknown and hybrid systems. Okay, so now it's going to get a little more technical. We will use control barrier functions to enforce safety. Control barrier functions are a nonlinear control design tool that proved to be really useful in our specific case. And I'm going to explain a little how this works. Who's familiar with barrier functions? Just asking. A few, okay. So like I said, we're assuming this system over here with a control input U. And let's now say or consider a function h that acts on the state of the system, for instance, the position, right? And this function h defines our safe set as the zero superlevel set of the function. So all states where our function is non-negative define basically our safe set here in blue. So now what condition do we need if we want to have safety? Well, that's quite simple, right? If our robot goes to the boundary, we need to be able to control it to either be pushed inside or to traverse along the boundary. How can we express this mathematically? We want that for all boundary states, there exists a control input such that h dot is greater or equal than 0. Okay. Why greater or equal than 0? Simply by the definition of our safe set, right? And then we have safety. So this intuition, we can formalize it by the notion of a control barrier function. Basically, we say that this function h is a control barrier function if we can find a u such that h dot is greater or equal than the negative of this alpha function. What is alpha? It's an extended class K function, so nothing really more than a strictly increasing function that's 0 at 0. The important thing is the 0 at 0, because on the boundary here, our function h is 0. So basically on the boundary, this term here will become 0, and we will recover exactly this expression here, and we have safety, okay? So for the specific case of the input affine dynamics here, which by the way model a large class of functions, h dot looks as follows. So we can write it as that. And the point I want to make here is that U appears linearly. So once we have a control barrier function, we can efficiently design a control law online, right? Also, keep in mind that I will refer to this constraint here as the CBF constraint. That's just some terminology. And like I said, if we have found, or if we can show that H is a control barrier function, then life is good. We have a safe control. However, what is the drawback? In general, it's very hard to design CBFs, right? And back to the point I made already before, can we instead learn these CBFs from data? Okay. Now, if we want to learn them from data and from expert demonstrations, we need to set up some data sets. That's what we're going to do now. So let's get back to our spaghetti trajectories here over here. And let's pick one data point denoted by xi. Okay. So what we're doing is we're putting a ball of size epsilon around this data point, which is exactly the orange region over here. Okay. And let's do the same thing for all data points that we have. And let's take the union over these balls. So what we get then is this orange donut over here. Okay. So this is basically the set of safe states, our orange donut, right? Additionally, what we need is a set of unsafe states. Okay, so what we're doing is we artificially sample unsafe states around the boundary of our orange donut. So we're getting these gray rings over here that we label as the set of sampled unsafe states. Okay, and there are computational methods how we can do this, boundary point detection algorithms. And now we have these two data sets, and we're basically ready to write down our constraint optimization problem. Just one more piece of notation before. We denote by Q basically as our CBF constraint, our H dot plus alpha from the definition of the CBF. Okay? And now we can write down our optimization problem that I'll walk you through briefly over now. So what do we want to do? We want to find a function H over there from a function class. Calligraphic H. And this could be the set of neural networks, right? But it could be any other function class. And we want to minimize the complexity for obvious reasons. And then we have three constraints that are really important. The first constraint basically acts on the unsafe states. So on all states that we sampled in this gray ring. And what we want to do is we want to push H to be negative over there. Okay. So for all states in here, H will be negative. And in fact, we enforce it to be strictly negative and upper bounded by the negative of gamma, where gamma is a positive robustness slab. Okay. The next thing we do is we look at our safe states in the orange donut over here, and we force that H in there is positive. In fact, we again enforce that it's strictly positive and lower bounded by this robustness slab gamma again. So what do we achieve by these two constraints? Basically, H in the orange donut here is positive, while outside in the gray region, it's negative. And by that, we shape the level set, the zero level set of the function H, and we define our safe set. So this is the intuition of these two constraints. The third constraint over here enforces the CBF constraint, basically that Q is also greater than 0 and lower bounded by this robustness slack. And we enforce that for all safe and unsafe states. Okay. Cool. So we've written down a constraint optimization problem. Let's assume we can find a feasible solution for now. Okay. So let's say someone has given us a function H that satisfies all of the constraints over here. Okay. Let's say we have gotten that. Under which conditions do we have we learned a safe control barrier function? Well, basically, if the data points are dense enough, if H and Q are smooth enough, and if the robustness slacks are big enough. How can we envision this, or can we put this in math? Basically, we want that the epsilon, so the size of these small balls, is upper bounded by our robustness lag over the Lipschitz constant. So that's kind of the conditions that we get here. And it's an interplay between, smoothness of in terms of H and Q, as well as density of data, like I said earlier. But the question is still, how do we solve this optimization problem, right? In general, it's a non-convex problem. But if we restrict our function class H here in a certain way, we can obtain convex programs. So for instance, if we parameterize our function H to consist, to be basically linearly parameterized in a decision variable theta over here, and if we pick some high dimensional function phi, then we get a convex program. And these phi functions over here could, for instance, be Fourier features, right? So expressive function classes. However, if we want to instead use neural networks, then what we're doing here is we solve the Lagrangian relaxation of our constraint problem. So we're transforming the constraint optimization problem into an approximate unconstrained optimization problem as follows. Basically, we want to take the constraint over here and put it into the cost function, basically by this max operator, and we multiply it with a Lagrange multiplier that we want to maximize over here. Okay? And we do this for each constraint. And then what we have obtained is, like I said, instead of a constraint optimization problem, an unconstrained approximate optimization problem that we can solve efficiently using stochastic gradient descent. All right. Cool. So let's look first at a toy example. I'll build up slowly to more complex examples. So let's assume here we have a decoupled 2D example that looks like that, right? So the thing is, we can feedback linearize the system even. And our control objective is here that we want to track the blue reference, and we want to avoid the red region over here. Okay, so this is what we don't want to end up into. What we do is we generate some expert trajectories in the following way. We use basically feedback linearization and then a simple tracking controller together with an analytic control barrier function that we know works already. So again, this is only about collecting data and showing that the level sets that we can imitate basically this barrier function. So what we get here is the set of safe states, which is here in green. Remember before it was the orange donut. And then we have the unsafe states in red over here. And we have in blue basically a buffer region, which allows us basically to learn a smoother control barrier function, which then allows us to satisfy these constraints, the epsilon over the robustness over the Lipschitz constant. Right? Okay, so what we did is we parameterized our CBF with 200 random Fourier features, so we get a convex program that we can solve efficiently with MOSEC. And these are the level sets that we get. Like I said, this is just a toy example, but I want to show you how the level sets look like the function that we have. So what you can see here, basically, the 0 level set is exactly over here, this ring. So this is the safe region that approximates the expert that the data that we had obtained before, right? And what you can see over here in 3D is that we have a really nice and smooth curvature of the barrier function that we have got, okay? So now, can we also check the constraints that I've mentioned? And yes, we can do that. That's basically the safe constraint. This is the unsafe constraint, and this is the CBF constraint. And we have, verified that they also hold, as you can see over here. So we have learned a valid control barrier function from expert demonstrations. Okay, right. So the next step is, of course, if we want to move to more complex systems, it's unrealistic to assume that we know the model, the system exactly, right? So in most of the cases, F and G are unknown. Right? But what we have in control is we have pretty good models, F hat and G hat, right? So what we assume here is that we can bound the difference point-wise between F and F hat and G hat by this delta F and delta G. So now the question is, how can we modify our constraint optimization problem to learn robust control barrier function? And it's actually pretty simple. Recall that before we had this constraint. So this was basically H dot. And for the input affine dynamics, it became exactly this expression and this alpha function. Okay. What we're now using instead is we will replace our F and G, which is unknown, by our models F hat and G hat. Okay. And we will keep our alpha as is, and we will add a robustness term to add for the difference in basically in the uncertainty that we have by not knowing F exactly, right? So we'll plug in the delta F and the delta G here that quantify the difference, okay? And what we did is we looked into this autonomous driving simulator called Carla. We identified a model for a car, and we used a built-in controller, but this could also be a human driver to collect expert demonstrations. And one of these expert demonstrations is shown over here. On the left-hand side. And on the right-hand side, you can see our learned CBF controller. And what you note is basically that the learned CBF controller closely approximates the behavior of the expert, which is exactly what we want. And by that, we get roughly the same safety guarantees, okay? So again, emphasizing here, we don't know the model of the car exactly, but we've used system identification to get a model and then learn a robust CBF. That does the job in this case. The good thing is we can also employ this CBF on different roads. So for instance, on this road over here, we haven't obtained any expert demonstrations, but since our training is in local coordinates, we can really use the controller also on different roads. And as you can see here, the car will also drive safely. Okay, so this is cool. So we can learn robust and safe control laws. But in most of the cases, you know that the state X is also not known, right? So X, and we don't have exact knowledge of the state at all times. However, what we may have is we may have high-dimensional output measurements. And I'm emphasizing here, we really need high-dimensional measurements. For instance, here, we may have a dashboard camera that is mounted in the car, right? In general, if we have a dashboard camera, then the function P is not known to us, right? But the assumption of high-dimensional measurements allows us to assume that there exists an inverse function to P that exactly recovers X. But of course, this function P inverse is also not known to us, right? However, what we may have, again, is an estimator, right? From input-output data. So we are using an estimator over here that gives us a predicted state. And what we're assuming is that the difference between the real state and our predicted state is, pointwise again bounded by such a delta T. Okay? And then we can learn perceptual CDFs. How does this look like in the constraint? Again, the constraint optimization algorithm is just changed by manipulating or changing the CDF constraint here. This is what we had before. What we're doing now instead is we will replace the state X just by our estimate in the first and also in the second term. So we'll get an X hat over here. And we'll again get a robustness term, right? To account for the error that we're making here in our estimation. And we plug this into, we exchange basically Q by Q perception over here, and then we can learn perceptual CDFs. Does this work? So yes, it does. Here, for instance, in this car, we collect these dashboard camera images. We resize them because these images are typically very big. And then we can do safe control from images over here. You see that the car stays safe, even though the control gets a little more jerky here, especially when we're going into the left turn. Yes?
So did you learn the estimator and the CDF separately?
Yeah. So you can use any estimator, basically.
Did you learn them separately?
Yes.
Separately. Yeah.
So you first learn the perception map, first learn the estimator, and then you use that in the learning of the CDF.
Is it possible to learn it together?
Probably, yeah, exactly. That would be a nice thing to really integrate it, because I guess the way we're doing it right now, it might be conservative. We really rely on,
That is the first step.
Yeah, exactly. Right. Maybe any other questions in the meantime? I didn't. Okay, cool. I'll just move on then. We can also learn yes.
Actually, I have a question. When you said user demonstrations, you should show only the case where the car is in the right path, or you also show like the bad cases?
No, just safe behavior. Yeah. So we really assume that we only have good behavior, no collisions.
And how does the robot know where the barrier is? Because it doesn't know like the network collide.
That's basically based on the experts, because maybe I can go back a few slides to illustrate that question. So here you have the experts, right? Let's say this is the car is driving in a circle. Let's assume that for a second, right?
I got it. So
it's the boundary of the expert data.
okay,
Yeah.
It's based on the data and not the actual environment.
Yeah, exactly. Yeah. So the environment doesn't matter. For us, we're thinking in state space, basically. Right?
Okay.
So here in this case, like this over here will be where the car will react to keep the system safe, and this over here. Okay.
Got it.
Okay,
I
cool.
also have a question.
Yeah.
So basically what you showed is to learn the expert behavior in one scenario. But then you showed another case that what it's learned generalizes another scenario.
Yeah.
Just to understand what's the source of the generalization. It's the problem formulated in a way.
Yes.
In a way, so that
Yeah. We train in local coordinates. So what we assume is that we have a path planner, let's say, that gives us a reference trajectory. And the reference trajectory, I think it crashed. No, it didn't. So the reference trajectory basically gives us, a path to follow, and we train with respect to the error. So it's called cross-track error. So it's basically the difference of the car to our reference trajectory and the difference in heading error as well. And by that, you can then use it on different roads, because if you train in local coordinates, it will be very difficult. Okay. If you, however, then have the perception map, it's way more challenging to generalize.
Yes.
Okay. So for state knowledge, it works really well. For perception map, it's a little more difficult. Yeah. Yeah. A what?
Reasoning. So if you have a local environment
Yeah.
and the expert data showed that there was deviation from the reference track,
Yeah.
and that is because there happened to be some obstacle.
Yeah.
So is it possible to learn that like the driving strategy, or basically like reactions?
Reactions. We haven't looked into this,
Okay.
so I can't really, probably, yeah. So for us, it's really just state space. But reaction, you could certainly, since we assume here that we also record the export action, you could certainly impose constraints on the export action to have reactivity, something like that. Yeah.
One quick question. So we do want to have the blue learned set be a strictly subset of the set S, right?
Yeah.
C. So do we want the best approximate from C to S, or we want C to S as much as possible?
This blue one, you mean you?
Right.
So you want the blue one to be as big as possible, but within
the S.
Yeah.
Okay.
So maybe that's a good point also to emphasize that, the volume of our safe set depends on how explorative our expert demonstrations are, right? Because here you see, all of this could be safe. We don't know what the dynamics there will be, but it could be safe, right? If we have double integrators or single integrators, we would be safe over here. But we don't have any expert data. So in that case, we render it as unsafe. And, if we have more data, we can also go there. Also mentioning this is like, I think I said this before already, we talked about it, that, data really gives us a feasibility certificate. Since we have data and these expert demonstrations, we have a feasibility certificate that this problem is feasible, basically, and then hopefully lets us scale in larger dimensions than the techniques that I mentioned in the very beginning. Yeah.
Do you have any assumption on the geometry or topology of state set that we're trying to learn?
No.
That you can make it as weird as you wish.
Yeah, exactly. So what we assume is just one thing, that the experts are epsilon far away from the boundary of the unsafe set.
So this shape is, because I can imagine that we have two shapes that they touch only at one point, and if the trajectory wants to touch from one to the other, they have to go to that small.
No, this is
So
not.
that cover goes to.
Yeah. So you're talking about this red region, right?
I'm talking about the safe set that we wish to learn.
Okay, so that depends on the function class that we're picking.
So
But we would like to have something that is smooth. So I guess the cases that you mentioned, where you have something that is maybe not as smooth, they would give us.
it could be smooth, but then properly shaped, maybe they have some geometric properties. So I would like to know that whether throughout the convergence group or convergence, that do you impose any constraints on that set?
No. There are no constraints basically. So if you have neural networks that are large, you can potentially get any shape of the safe set.
But then you would assume that your set belongs to the possible achievable or the learnable sets.
Yeah.
So that would pose a condition that I would have to make sure that what I'm trying to learn can be expressed as say as a summation of a set of basis elements.
Yeah, true.
So there's some sort of a structure there.
Yeah, exactly.
It is not arbitrary.
To me, it really depends on the function class that we're choosing.
Right. That I agree with. But then once you fix your basis,
then there's no
then
restriction.
what we can achieve is what we can do.
Yeah, exactly. So after you fix the function class, there's no other restriction that you're imposing, basically. Maybe we can also talk about this offline, but I think, I mean, the thing is that it may get conservative depending on the, yeah, depending on the learning. Let's say, but there are no restrictions.
Question about the previous one.
Yeah.
You have the epsilon term.
Yeah.
To get this, right? But depending on the epsilon or even depending on the trajectories, your set might not be compact, right?
Exactly. Yeah. So that's the trade-off. If you have a very small epsilon, you get Swiss cheese. So you get a really weird safe set. So what you want from a practical point of view is you want a large epsilon so that you don't get Swiss cheese. And that then basically requires, if you have a certain, well, from a practical point of view, you don't want Swiss cheese, and this gives you a lower bound on the epsilon. Then you basically know what robustness constraint you may need and how smooth the function should be. Right. So also related to that, I want to maybe mention one thing. I didn't put it initially because what I'm doing here is I'm enforcing that H is negative here and positive there, right? So at the boundary, basically, you cannot satisfy the constraints because you're going from strictly negative to strictly positive, right? So what we're doing is we're inducing a buffer region over there from a practical point of view. And then we'll shrinking your safe set. Okay. Yeah, so this also plays. Did it answer your question with respect to the epsilon? Okay. Also, of course, the constraints that I've shown over here, you can pose them in terms of local Lipschitz constants, right? And you can have different gammas for all the constraints, of course, right? But for the sake of the presentation, I kind of highly simplified it. All right, cool. Let's get back to our hybrid walker. So basically, this was what I mentioned. I mean, here, this buffer over here allows to learn a smooth CBF that is also feasible, because if you go from strictly negative to strictly positive, you won't be able to satisfy it. If you induce a buffer over here, it's possible. All right. Okay, so we can also learn these safe control laws for hybrid systems. And we're in particular using here the flow jump formalism by Ricardo Sanfelice. For those of you who are familiar with it, bottom line is we have a flow set in which the system can evolve continuously, basically by this ordinary differential equation. And we have a jump set where discrete events may happen, right? Like I said, like when we have a hybrid walker and the foot hits the floor, there's a discrete event that is described by this jump map, and the state at that point is described, by the jump map. Exactly. Okay, so this hybrid walker over here is walking down an inclined ramp, and we can control it in the hip joint and in the ankle. If we don't apply any control action, as you can see here, the walker will fall down, basically, right? So there's only a very small region of attraction where you have a safe walk, and mostly the walker will fall down. So what we did was we used an energy-based controller from the literature to collect expert trajectories, right? So we just, from Bruce Tedrake, we used an energy-based controller and we rolled out a lot of trajectories. And from that, we learned a 2-hidden-layer neural network, a fully connected one. And we applied it on this walker. And as we can see here, the walker is safe. The correcting control actions are shown in green in the hip as well as in the ankle. Okay. What I also want to show is a bit more of a statistical evaluation over here. On the right-hand side in this figure, you see the expert energy-based controller. On the left-hand side, you see our trained controller, right? Every dot over here indicates an initial position of the system. So an initial position of the left swing foot. If the dot is blue, there were more than 10 walks, so we classify it as safe. If it's red, the walk is unsafe, basically less than 10 walks. What we see over here is that the safe set has this shape, and that most of the points in this safe set are safe. There are 3 or 4 instances where we have unsafe walks, and this is most likely because we haven't collected enough expert demonstrations, right? What is interesting, though, is that in this region over here, we're having a lot of safe walks while the expert here is failing. And the reason for that is basically because of the gamma, because of the robustness that we induced into the learning, so that we're more robust than our expert controller. So in fact, you can show that by this gamma, you achieve that the safe set is attractive. And by that, you get these nice properties. All right, and by that, I'd like to wrap up the first part of the talk. Just in summary, we learned safe control laws from expert demonstrations and using partial model knowledge. What we're working on currently is how can we do this for changing environments? So for instance, if we have perception, but the weather conditions change, like how can we accommodate this distribution shift? We're also looking into a hardware implementation, and we want to learn distributed control laws. There was a question.
Sorry, now that you mentioned before the private system where you have like continuous and discrete dynamics, I was just wondering if you can also model those barrier functions for the discrete space.
Yeah, you can. Yeah. For discrete, it's just a simple recursion. Actually, you only need that v of x of t plus 1 is greater or equal than 0. So when you put the dynamics in there, you have a very simple condition. Yeah, we can do that. All right. Cool. So, okay. So far we have talked about how can we design systems, how can we design safe control laws, right? And what I want to focus on now is a bit more, how can we assess robustness of autonomous systems and how can we verify their safety, okay? So we'll not talk about control now, we're more talking about analyzing systems. And I particularly here want to focus on temporal robustness as opposed to parameter or model robustness, which is a certain case of spatial robustness. So in spatial robustness, you're talking about tubes. I guess all of you know tube MPC. We want to focus on temporal robustness. Okay? All right. And since we focus on temporal robustness, it's natural to also look at time-critical systems, where time-critical systems are really systems where not meeting stringent real-time constraints can have catastrophic consequences and again result in loss of life or in property damage. I've shown a few examples here. Air traffic control is one. Autonomous driving is an example. We talked about platooning before is an example where timing plays a role, emergency delivery, and also automated or semi-automated warehouses. So in particular, time-critical systems are systems that are connected, and also multi-agent systems are time-critical. So what are potential reasons for failures in time-critical systems? There are many in the end, right? If you look at the standard control loop that we have, a network control loop, we have the plant over here, we have an actuator, a sensor, a network, and a controller, right? And we can have delays in all of this. We can have delays in the network, in the communication, we can have delays in the computation. We may have scheduling algorithms in there that may be subject to delays, but we may also have delays in actuation. Okay. And in general, we may have delays in connected systems if we look at cars or if humans are involved. So there are many reasons why we may have uncertainty. This is also what Elon Musk said about jitter, which are the
latency. And actually, jitter is more of a challenge than latency, because latency is like you can anticipate and predict. But if you've got a stack up of things going from the camera to the computer, through then a series of other computers, and finally to an actuator on the car, if you have a stack up of tolerances, of timing tolerances, then you can have quite a variable latency, which is called jitter, and that makes it hard to anticipate exactly how you should turn the car or accelerate, because if you got maybe 150, 200 milliseconds of jitter, then you could be off by up to 0.2 seconds, and this could make a big difference.
Okay, so he's basically saying what is written in this diagram over here, right? If we have a stack up of these timing tolerances, and if there's randomness involved, then we have jitter, and this is a problem in autonomous driving. Okay. So robustness against timing uncertainty is really critical. And the question is, how can we analyze and how can we define temporal robustness? And surprisingly, there's a lot of literature on spatial robustness, tubes, and so on and so forth. But there's very limited study about temporal robustness, also in the formal methods community that some of you here are working in. Okay, so now what I'm going to do is I want to give you two definitions of temporal robustness that we have worked on. Okay. let's assume, in order to define these two definitions, this simple example over here. So we have a signal x, okay? And this signal has two components, x1 and x2, here in red and in blue, okay? So we have two subsignals that make x. And we have the following specification. We define the function h over here as 1 minus the absolute value in the difference of the first and the second component. And what we want is that for all times in this green region, so from 145 to 155 seconds, we want that h is greater or equal than 0. So for all times over here, we want that the difference in the first and the second component is smaller than 1, okay? So that's our specification. And I've plotted h over here, and you can see this is above 0. So we satisfy the specification given this, these two signals, basically, right? Okay, one piece of notation I want to introduce is the satisfaction function. Again, the temporal logic people will know what this means. It's basically this function is 1 if this specification is satisfied. So if we take the minimum h of x over this time interval, and if it's greater than 0, okay? So if we satisfy the specification, we have a 1, a Boolean 1. If we violate the specification, we get a -1, okay? So just piece of notation, keep beta in mind. Okay, the question now is how should we define temporal robustness for this example? First, we want to define something we call synchronous temporal robustness. And this is the most straightforward definition. In fact, in time delay systems, they use a similar definition. So what is the idea? Basically, we want to shift x, our signal, in time until the specification is violated. So we're shifting the signal, the first and the second component by the same amount, right? So let's do this. First, let's shift both components by 5 to the right, okay? So this signal basically moves by 5 time units to the right, which is indicated over here. And as we can see here, the specification is still violated. The black curve is still above 0 in our region, okay? So let's shift it a little more, by 12. And we see now the specification is still satisfied, but we're close to violating it. And if we shift by 1 more, then we have that the specification is violated because at this point, h is negative, all right? And this is what we call synchronous temporal robustness, because basically we're shifting the whole signal and all its subsignals by the same amount. And the synchronous temporal robustness for this example is exactly 12. So we can shift starting from here, we can shift the signals by 12 to the left or to the right while still having satisfaction of our specification, all right? How do we define this in math? Basically, we want to find the maximum tau such that for all time shifts that are smaller than tau, we retain the satisfaction of the specification, okay? So that's it looks intimidating, but it's really nothing more than finding the maximum time shift, okay? So now what may be the drawback of this definition? I mean, certainly in some applications we can use it, right? But the drawback is really that you shift here both signals by the same amount. And in distributed systems, let's say we have 5 robots, right? One robot may be delayed by 5 seconds, another one may be delayed by 2, and another robot may start 2 seconds too early, right? So what we want to do is we want to shift these subsignals here, these components, asynchronously, okay? So let's do that. I mean, now the idea, like I said, is to shift the first and the second component in different directions or by different amounts. First, let's do this first. Let's shift the first component by 1 to the right and the second component by 1 to the left, okay? We still see we satisfy the specification over here. So let's shift a little more. Let's shift the first component by 3 to the right and the second one by 2 to the left. And we see here, we still satisfy the specification. Now, if we shift a little more by 4 to the right, the first component, and by 3 to the left, the second component, we see that we now violate the specification. So in fact, in this example, it turns out that the asynchronous temporal robustness is 3. So we can shift each signal by at most 3 to the left or right. We can, and individually, okay? But if we pick 4, we may violate the specification. And we can again put this in math. We can define the asynchronous temporal robustness as follows. We want to find the maximum tau such that all individual time shifts that are smaller than our tau still satisfy the specification, okay? And these are the two notions that we have. So now we have several properties that follow directly from this definition that allow us to quantify the permissible timing uncertainty that our signals may have, right? So first here, when we look at the synchronous temporal robustness, and basically the absolute value of this defines the permissible timing uncertainty that we have in synchronous time shifts, okay? It's just natural by definition. And for the asynchronous temporal robustness, we can, it quantifies basically the permissible timing uncertainties in individual shifts, again, following by the definition directly. What we can also show is that the synchronous temporal robustness is an upper bound to the asynchronous temporal robustness, okay? So this may be useful because of the next bullet that I put up, because of the computational complexity to calculate these values, right? If we look at the synchronous temporal robustness, it scales with O of 3, where 3 is the maximal desired robustness that we have. However, for the asynchronous temporal robustness, we scale exponentially in the dimension of the state, okay? So there may be reasons why one wants to use the synchronous temporal robustness over here and use the property that it's an upper bound to the asynchronous temporal robustness because it's easier to compute, okay? But just keep in mind, I mean, the asynchronous one scales exponentially in n, while the synchronous one only scales polynomially in the maximal robustness that we're investigating. So let's look at an example. The scenario over here is the following. It's a T intersection. We have 3 vehicles that want to make a turn. Their velocities are fixed for now, okay? And the specification that we're looking at is that when the green car is in a 10-meter radius of the center of the road over here, we want that the distance between the red and the green car is larger than 15, and the distance between the blue and the green car is also larger than 15. Okay. So that's the specification, a Boolean specification that we have imposed here. Now, on the left-hand side, what we will see, there's an animation, is that all cars start at the same time. Okay, so it's a nominal scenario. On the right-hand side, you see that the green car basically will start too late, 12 time units too late, while the red car will start 12 time units too early. Okay, so let me start this. What happens? And the constraint satisfaction is basically shown over here, the safety constraint. Okay, so what you see is that basically, yeah, exactly. So this is the point I want to highlight, that when the green car is within 10 meters of the center, the red car, since it started too early, just naturally arrives earlier, right? So in this case, the specification is violated. And for this example, for this one here, the asynchronous temporal robustness is 11. Okay, and I've picked here an example where it's 12, where we violate the specification. Okay, so this is just another simple example to illustrate the principle. Let's now look at a more complex example using signal temporal logic. Some of you may be familiar with the notation, but I'll walk you through it briefly. We have 2 robots over here. Basically, robot 2 starts in this region and robot 1 starts in this region. And we want that these robots eventually, within 2 hours, robots 1 and 2 should recharge for at least half an hour, right? So they should, within the first 2 hours of the mission, go into this region and be there for half an hour. Okay? What we also want is that within 1 to 6 hours, robots 1 and 2 should be in region B, for instance, to do a collaborative task, right? They should be there simultaneously at the same time. And we want that within the first hour and within 1 to 5 hours, robot 1 or 2 should be in region A, right? So in this time frame over here, one of the robots should be in A, all right? So this is a more complex specification. And as you can imagine, then timing plays more of a role. In the nominal scenario, which plays now, you can see that basically the STL specification is satisfied, indicated by the green color here in these subplots. We see basically robot 2 recharged initially, then robot 1 recharges. Here, robot 2 is basically in region A, and then eventually they're simultaneously in region B, okay? All right, so this starts a little too early. Let me just start it. So then we want to analyze the synchronous temporal robustness, which in this case, we can calculate it, it's 7, okay? So what we're doing is we're shifting the initial position of the robot by 8. And what you can then see is that the specification, that was too quick. I think it disconnected again. 1 second, I'll reconnect. So it seems like when I play videos that then the app crashes. Okay. And share. Yeah. By the way, am I running out of time? Is it? Okay, yeah, I'll hurry up. Yeah, okay. So basically here you see that the specification is violated and the asynchronous temporal robustness is 6 in this case. So if we shift individual robots by 7, we see that here in this case, they will never be in region B simultaneously. Okay, so just another that we can handle more complex specifications in terms of STL and calculate temporal robustness for them. So now the next question that I'll cover in the next 5 minutes is, what about stochastic systems? Because once we employ systems in the real world, we'll have stochasticity, right? We will not only have one signal, but we will probably have a couple of realizations, right? So here, a car overtaking the black van, we may have just, many trajectories. And the question is, can we analyze temporal robustness also for stochastic systems? And this is what we're doing here now, and we advocate to use risk for analyzing stochastic systems. And this is basically motivated by the fact that both the scientific community as well as from a more practical viewpoint, people have asked for risk-aware, decision and control frameworks. In particular here, the NTSB, the National Transportation Safety Board, in connection with an Uber accident, stated that basically the reason why there was an accident was Uber's inadequate safety risk assessment, and that they state the need for safety risk management requirements for testing autonomous vehicles on public roads. And here is also a special issue of the Journal of Artificial Intelligence that highlights this. So can we assess risk in terms of temporal robustness? Okay, that's the question. In order to talk about risk, I'll briefly introduce risk measures. They basically can be defined over a cost distribution. For instance, assume here that the blue distribution is our cost, for instance, the cost of failure, right? And a risk measure you all know is the expected value, okay? And you might also all know the worst case, which may be conservative. So I want to now argue that we should particularly be interested in tail risk measures, such as the value at risk or the conditional value at risk. For the following reasons, why not use the expected value? Basically, if we use the expected value, we may have very good performance as over here, but we may not be safe, right? Then the question is, why not use the worst case if we're interested in safety? Because simply then the roads would be empty, right? We would be safe, but no one would be driving. So inevitably, we need to look at tails. And that's what we're doing here. Tail risk measures can be used as a tuning knob between average and worst case cost. Okay. How do we define the temporal robustness risk? Basically, we want to quantify the risk of lacking temporal robustness, right? Here, a short example again, we may have that the service needs to be provided within this time frame. Then temporal robustness is nothing more than the distance from when the service gets enabled to the deadline, right? And for stochastic systems, we get various realizations of the system, and they all map into a robustness distribution. So then the idea is simply to put a risk measure around the negative of the synchronous or the asynchronous temporal robustness. Why the negative robustness? Simply because robustness is something good, and the negative robustness then becomes our cost function. Okay? And we can do the same thing for the asynchronous temporal robustness. The question now is, can we compute this? And in general, we can't. So there are some subcases if we make some assumptions where we can exactly compute our risk, right? Gaussian distributions, we need to discretize maybe even, but in general, we cannot. But what we can do is we can estimate it from data, okay? And I'm gonna skip over a few details here. I'm doing it for the value at risk. we can build an estimator that is basically based on an empirical CDF of our negative robustness, and we get a term over here that scales that we basically want to be small. And how do we achieve this? We collect more data, or we allow a higher failure probability. And the guarantees that we get is with a probability of 1 minus delta, our estimator here is an upper bound of our value at risk. We can also get a lower bound. I'm not showing this here, because I want to show this short example before I wrap up. We again look at the car over here, and what we do now is we let the initial time of each car be uniformly distributed within D, where we can select D. Okay? So for different Ds, we basically get different risk estimates. Naturally, when we don't have any delay, then we get a very good good risk. So negative values here are something good for us, right? And we can also see that the estimates are tight. Basically, here's the upper bound, here's the lower bound for the 5% quantile, and here for the 2% quantile. And you can see that the difference between the upper bound and the lower bound is low. And the estimates tell us also how much timing uncertainty we can sustain. Again, if we're basically looking over here and we have a robustness of -10, then it tells us that we can sustain 10 time delays. So if we go to this column, to this row over here, we see that this holds this up. Okay. But I don't want to go into details here because I think I'm running out of time. One thing I wanted to show is we can compare scenarios also in terms of their risk. I think that's an important point to make. Here, basically, we have scenario 1, where the blue and the red car have certain velocities. And then scenario 2, we just flip their velocities and we put some noise on top, right? Then we let the cars drive and we estimate the asynchronous temporal robustness. And that's the last point really I want to make, is that we get these distributions for the temporal robustness, for the asynchronous temporal robustness values. And if we go by expected value, the scenario 1 would certainly be the better choice. But scenario 1 over here has a long tail of non-robust realizations. So in that sense, if we look at the higher tails, the second distribution, the red one, will be better, which is more Gaussian shape without a long tail. Well, and with that, I'd like to conclude. We defined risk for temporal robustness, and these were the papers that I used for today's presentations and the people I worked with. Thank you for coming.
Can you go back to page
16.
16?
Okay. Yeah.
I have one question, but I would rather just make one.
Sure.
So when you
Latency. And actually, jitter is more of a challenge than latency.
Why is so sorry? I don't know why that video was playing.
just in the bottom that we were holding that to the run function.
Yeah.
So there are many different examples about run function.
Yeah.
So the most famous one, or the dual function.
Mm-hmm.
So one, the normal way that we will form the Lagrange dual, and then here's a different way of doing that. Right?
Mm-hmm.
You would form your dual function, your penalty function, which is in this format. You would take the summation of the maximum of those two quantities just to make sure that when you find an x, your x is going to be a simple function. By using this penalty function, you can compute the dual problem, right?
Mm-hmm.
So one thing that I would like to mention that, you can take a look. Your primal is non-convex, right?
Yes. Yeah. In general, yeah.
So when you form your penalty function, this form that we have written, if you minimize it over x, you're going to get a dual function in terms of the lambda, right?
Yeah.
So for a non-convex problem, we know that there's a duality gap.
Exactly.
For this case that we have written, the duality gap is 0.
In this one, you mean?
Yes, for this one.
Okay.
So I have a paper with George back in 2008 or 9 or 10. We submitted to ICRA. In that paper, we showed that for this sort of dual problem that we form by using this, the duality gap is 0.
Yeah, I would love to look into that because for now we haven't really. Yeah. George is not on these papers though, so
okay.
maybe he should be.
So in that case, that's a good news, I would say.
Yeah, I will reach out and yeah.
So for this, you're gonna have a zero robotic gap. What that means is that your goal is always economics problem.
Yeah.
You solve it, you can recover the solution of this problem exactly.
Okay. That's great. Yeah, I would. I will take a look definitely. Yeah.
Like for this project, the key concept is the expert demonstration, right? Is there any like mismatch between the agent and the expert, for example, and like Uber using Toyota and you are driving BMW?
We assume that the experts drove exactly the car that we want to drive. But this is also an interesting like robustness question, right?
You can consider adversarial learning.
Yeah.
And you can adapt it to different parameters.
Yeah, exactly. So really, I mean, there's the whole ton of things one can consider for the expert, also in terms of soft constraints, maybe, right? I mean, for us, it's really safe or unsafe, and like the expert they have driven the same car, right? Yeah.
I have two questions. The first one is like, I consider like in the STL, the usual way to define robustness was like robustness over the signal, not over the time.
Yeah.
Like
over tubes, right?
Yeah. So why do you consider robustness over time will be like better? Or
not better. It's a different way of forming. I think for different systems, different notions of time may be important. So for me, like temporal robustness, like I said, is really important if you have distributed systems when there are delays involved. While spatial robustness may be particularly of interest if you have two cars on a lane and you don't want them to collide, then you're interested in spatial robustness. But once they're doing a turn, temporal robustness may be interesting again. And in fact, I mean, you can combine them or try to combine them, right? This is something we're also thinking about. How can we combine spatial and temporal robustness? There's one paper by Donce, I think, who does that in a way. Are you familiar with the Donce paper? Yeah, I can show you later.
And the second one was what I was asking before, the discrete like dynamics, the way you define the control pattern functions, because I think like the three requests that you have, like the smoothness and density of the data and everything, will not be the same. So
it will be, because you will still have a function h that you want to be smooth.
Oh,
yeah. So the thing is, let me maybe go there too. Yeah, I didn't introduce hybrid systems formally because I guess I was already running out of time. I mean, I knew this was a long presentation. So basically, the function g over here will still need to be continuous in a way, right? It's just the set over here that allows you to do discrete jumps. Right?
oh, so the jump map is going to be continuous.
Yeah. When the jump map is discontinuous, there is no way you're going to get any guarantees, at least with our approach.
Oh, that was what was.
Yeah. No, you need like some continuity in F and G. Otherwise, I mean, your system may change, in a small region by a lot, and then you can't generalize. Yeah. Correct. Yeah. With what? With the donuts, I see. The famous orange donuts, right? Sure.
So my question is, how the value of gamma will affect the width of the orange donut shape? Will it affect the larger gamma or smaller?
So the thing is, there's this practical concern that the larger you make the gamma, the more likely it is that this optimization problem is infeasible. Right? So we need to introduce a buffer region in practice. That's actually what we do in all our learning frameworks. Let me go to the example in all our examples. This is really slow. So here, basically, since we choose a larger gamma, we need more of these buffer states. Because again, otherwise you're switching from H greater to gamma, then H smaller than minus gamma.
Right.
And then H can't be continuous.
Yeah,
So what we're doing is we're introducing this buffer zone over here, and we're enforcing H greater than gamma only here, and H smaller than minus gamma only here. And then naturally the zero level set will be somewhere in here, which is still safe because we know that this region over here is still safe. It's still expert space. So what we're doing in practice is we're having our experts from the car. We run some boundary point detection algorithms. There are some computational methods. And then we subtract a thin layer of them around that we label, where we don't enforce any H smaller or greater than gamma.
So generally speaking, the larger gamma usually indicates a safer region.
Yeah.
Inside,
Yeah.
But the less visibility.
Yeah, exactly.
So
And in order to address this less feasibility, we need to introduce conservatism.
Right.
Because this will not be safe in that case, or just parts of it will be safe, right? So yeah, the larger the gamma is, the more conservative we are, but the less, the more likely it is that we satisfy our conditions in terms of density of this data and smoothness of the function H and P.
So a quick follow-up question. So have you considered the uncertainty heuristics? They are all like continuous, like deterministic.
Yeah, there's everything to know.
Okay.
You mean in terms of the system dynamics?
Yes.
Yeah, here everything is known. That's why I called it toy example.
Okay.
Yeah. No, we know the systems exactly, and we construct. I mean, the safe region here is very easy, right? So we can get an expert basically by writing it down on a piece of paper and then get trajectory data for free.
Thank you so much.
Thanks for the invitation.